Right. So I guess you can see. Okay. So maybe I should. So I can see the chat and people. Good. Okay. So what are we doing at the moment? We are discussing the division algorithm. So we have a polynomial ring over a field in finitely many variables, and we try to create some sort of division with remainder. And what we did, we defined a reduction notion. So let me recall this a little bit. So I have a finite set of polynomials, of non-zero polynomials. Okay, polynomials over a field, and then I fix some term order, fix term order. Okay, and then I take some polynomial f non-zero, a non-zero polynomial, and I defined what is a one-step reduction. So I defined what this means. So one-step reduction. Mod f. So I hope you remember. I mean, maybe I can explain in words what we do. We look at the leading term of the polynomial g. Okay, g is, sorry, yes, g is also, no, sorry, I did it wrong. We look at the leading terms of these polynomials, okay? Okay, and then we try to find the term of f, which is divisible by the leading term of fi, okay? So if you can find the term, so if we have a term of f, such the leading term of fi divides t, okay, then I subtract from f a suitable multiple of fi, okay, so that this term t is cancelled. So what I create is something like, okay, fi, I multiply it with some term, okay, maybe u is a term, and then maybe I have some coefficient, okay, u is a term, this is a coefficient, and I form this. So to cancel term t, maybe I don't write every formally, but that's the idea. There is this term t, okay, comes in f with a certain coefficient, and I want to kill it. This is what we do, okay? That was the important thing. And then by doing so this was the one-step reduction, one sees that the polynomial g that we create is always smaller than f. So you should remember that the term order was defined on the set of terms, okay? But then we generalize to polynomials, okay, by doing kind of a lexicographic ordering. So if I have two polynomials and I compare them, I first, what do? I compare leading terms, okay? Okay, if one has a larger leading term than the other, then it's called larger. But if the leading terms are equal, then I forget about them and go to the next largest terms and compare those, etc. So it's like a lexicographic extension of the term order. Okay, and this is exactly what we have here. So you see, so why is g smaller than f? Right. So let's see. Maybe look here. Sorry, I should not cancel it. So it may be that f and g have the same leading term, okay? Because what I have eliminated, this term was smaller than the leading term of f, okay? Right, okay? But then I look at the next term, etc. So f and g, they have the same term. So if I order them in my term order up to, until I arrive at the term T. Okay, and the term T was there in F, but is not there anymore in G. So that's why F is larger than G. Okay. I hope this is more or less clear. Okay, then we had the no, right. So maybe maybe I also write this again more. So what we have, I already said it, but I think I want to write it because it will be helpful. So, okay, so more formally, F reduces to G modulo F if and only if there is a T in TF such that T is in the monomial ideal generated by the leading terms of F1 up to FR. So I use this symbol with these brackets. I use this. Okay. This in English, eckige Klammern. So to denote by this the monomial ideal generated by these terms. Okay, and this is exactly what this means. There is, now we see, I had it already. This means there is a term T. Okay, I could put a quantifier here. Okay. So, and there is some I, maybe I can also put, say, an index I such that this holds. But this exactly means this. Okay, this means there is an I such that the leading term of Fi divides T. So this is exactly that. Okay, so then if we cannot perform a one-step reduction, we call F a normal form. So F called normal form. Normal form mod F. If, okay, there is no G, this is not there, there's no G that such that F reduces to G. Or, okay, F equals 0. Okay. So, you know, normal forms are very important in mathematics. I mean, you have seen in many situations, for instance, you have a matrix and you're allowed to carry out certain operations like row and column operations, and you want to get a simpler form of this matrix, a normal form. For instance, you can put such a matrix to diagonal form. Okay, and then the diagonal are just entries 0 and 1. This you know from linear algebra. This is an example of a normal form, but there are many examples. So normal forms really are important. Okay, right. So then what we also defined is the m-step reduction. I can just make several one-step reductions in a certain order, then I get the m-step reduction. Okay, m is a natural number. Okay. And if I don't want to specify m, I just write the star. So it means there is some m such that this holds. Okay. Right. So these are these reductions. There is no algorithm so far. Maybe a remark. So if I have, a reduction from F to G, and H is a monomial, then F times H reduces to G times H mod F. This is very easy to check. Okay. Okay, you check it for yourself. Okay, so it's in a way, this reduction is compatible with multiplication by monomials. Okay, now I'm ready to state a lemma. So first, I rephrase what it means for a polynomial to be a normal form. Actually, we had this. Let me write it. F is a normal form. Mod F. If and only if. Okay. No, okay. I just have to look what we have here. Here, if you see, here I expressed what it means to have a reduction. Now, this cannot be possible. So this means there is no term of f which is in this monomial ideal. So I can just write it this way. The set of terms of f is disjoint from the monomial ideal generated by the leading terms of the fi. So this is empty. Okay. Okay. In the monomial ideal generated by the leading term of the fi, I can't find a term of f. So this means normal form. Okay. Then actually I proved this already. This is already clear. Next statement is any polynomial reduces to a normal form. Any polynomial f reduces to a normal form. Mod capital F. And here we know the proof already, because I mean, we take f, we try to reduce, etc. Okay, until we hope at some moment it will stop, so we end up with a normal form. So the only situation when this could not happen is then we would have an infinite chain of reductions. Okay, but then we would have an infinite chain of polynomials that get strictly smaller because of that. Where is it? Okay, because I said, okay, when I reduce, okay, when I reduce, I get the strictly smaller polynomial. But we proved last time that there is no infinite descending chain, strictly descending chain. This is this well-ordered property, okay? So, right, I think I will write something about the proof, but I explained it already. Okay, third statement, that's also important. So let's assume I reduced f to g. Okay, then I can always, I have such a representation. I have some coefficient polynomials ai, such that f can be written as a linear combination of the fi plus some g. Okay, there is some g. So I think of the idea is that the g is something like the remainder. Okay, so this is, I think of it as a remainder. Okay, and I have additional information on this coefficient. So this coefficient polynomial is ai that cannot be anything. I can somehow control their size in a certain way. So what I can say is that the leading term of all these contributions ai fi are less than or equal the leading term of f. So of course, if ai is non-zero, otherwise it's just not there. Okay, so in particular, I see f is congruent to g modulo the ideal generated by f. So the ideal generated by the set of polynomials f, I write with these brackets. Okay, so this stands for the ideal. Maybe I should write, this is ideal generated by the set of polynomials f. Okay. Okay. So let me prove this. Okay, proof. I think 1 is already done. Okay. 2, maybe I just write well-ordered property. So this was okay. I refer to the result we had on Tuesday. And 3, okay, this requires a little bit of work, but not much. So we can do an inductive proof because I introduced this notion of m-step reduction. So I can make an inductive proof. Now I show, okay, if I have a reduction from F to G in m steps, if I have this, then, okay, blah, 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 this property holds. Okay, and I show this by induction on M. Okay, and for M equals 0, there's nothing to do. So let's assume M is greater than 0. Okay, so, right, so, sorry. So I can assume I have, okay, let's do it this way. Right, I think I want to have greater or equal 0. So let's assume I have an m-step reduction from F to H. And then I reduce H to G in one step. Okay. Okay. So what is important to understand what happens here in this one-step reduction? What happens here, we know by induction hypothesis. So let's look at this. Okay, so actually I explained before the one-step reduction, so I think write it this way. I can now express H as, okay, mu is a field element, S is a term, Fj plus G for some mu in K. S is a term S. Maybe I can write it this term S and rest some S, some J. Okay, so the idea is that what happened here, okay, what happened here, we subtracted from H a certain monomial multiple of Fj in order to kill a term. Okay, and then I get exactly this. Right. I know, okay, the leading term of Sfj, okay, I claim this is less than or equal to the leading term of H. So the best is, okay, if you don't see it, the best is always to have this pictorial description. So you have, okay, I like to see it this way. Okay, maybe I put dots here, maybe to have it in color, I don't know. So my dots, okay, stand for the terms. So I have here H. Now here, this dot is for the leading term of H, and the other terms are smaller, okay? And when I do this one-step reduction, what I do, I kill, okay? There is this term to be killed. Okay, you see I subtract something. And I mean, here, what happens, okay, I have all these nice colors. When I do my subtraction of the multiple of Fj, I mean, this red thing is gone. And here, I mean, there may be changes, okay? There may be certain things may change, okay? But you see, in this situation, the leading term, okay, what do I want to say? Okay, the leading term of Sfj actually is the red thing, okay? The leading term of Sfj, the red thing, it's clearly smaller than the leading term of H. But in this picture, you understand a little more. I mean, like this part is unchanged, and here things are changed, and this is killed. Okay. Of course, it may be that this red thing happens already here. Then you kill the leading term of h. This can also be. Okay. Okay, I hope I explained this. So I best understand it in terms of pictures. So this was the one-step reduction. Now we apply induction hypothesis. Induction hypothesis gives me, I have a representation of this form. Okay, with where the remainder is h. And I know the leading term of AIFI of all of these is less than equal to the leading term of F. Okay. Now I just have to combine this. What I do now, I plug in my formula for H here. Okay. And then I rearrange a little bit. Okay. Okay, maybe I do it in steps. Let's do it slowly. Okay. So then I have here the sum over all I different from J plus here I have AJ plus mu SFJ. Okay, plus G. Okay. Okay, so I get the representation as desired. I only have to check that this guy here, the leading term is less than or equal than the leading term of F. But the leading term of this sum is less than or equal than the maximum of the leading terms of these two contributions. That's always the case. So in a way, this is like if we would work with the ultrametric, if you have ever encountered this notion. Okay. Okay, and this is, I claim, less than equal. So what do we know? If you see here, so this less than equal to the leading term of F, and here, okay. Sorry, there's something fishy here. Right, HJ, FJ, SFJ, right. And here, this is less than or equal to the leading term of H, but the leading term of H is less than or equal to the leading term of F. So I get this, sorry. Maybe since I write leading term of H less than equal leading term of F. Okay. Right, and this is the proof. So any questions on that? Or? So what I'm doing now is is rather combinatorial in a way. Okay, it's combinatorial at some point a little bit algorithmic. Okay, it's quite concrete what we are doing. Okay, no questions. So what we can do now, we have a polynomial and then we reduce until we arrive at the normal form. But it's important to observe that in general, this normal form is not uniquely determined. Okay, this is a very important warning. Normal form in general, okay, in general, not uniquely determined. So I can give a very simple example which causes no work to see. Let's see, f just has the polynomial x and x plus 1. Very simple. And then I say f is x plus 1. Okay, now there are two ways, at least two ways to reduce. So I can, on the one hand, I can say I can reduce my f to 0. Actually in one step. Okay, but 0 is a normal form. How can I do that? Well, the point with this reduction is always which of the polynomials to take. So if I take this polynomial, okay, I compare here the leading term is x here, okay, then here is the term is x, and then I just I subtract x plus 1 minus this, I get 0. I get it in one step. Okay. On the other hand, I could say I'd rather use the x, then I end up with 1. So if I say, okay, I want to take this one, then I subtract x, I have 1. So this is very annoying, and one may have the impression that this is not a very useful concept because of that. So how useful can it be? I mean, if it's not even unique, okay? Okay, but the point is, in some situations when we have a Gröbner basis, it will be unique, and then everything is good. Okay. So, right. So, because I also want to talk about a little bit about algorithms, and now it's important to note that we have arrived at the division algorithm. So you see, okay, where is it? I have my collection of polynomials. And when I want to do a reduction, I mean, I have to say in which order we have to look at these polynomials. Okay, I have this, and then I have a polynomial I want to reduce. So what do I, if I have fixed, if they are ordered, so if, okay, if I order them, ordered, I've already numbered them. And then I say, let's first look at the leading term of F1. And let's see whether it divides a term of F, okay? But this, I have to make it unique. So I take the largest term, which is divided by it, if there is one, and I kill that. And if this doesn't work, only then I go and try with the leading term of F2. Try first with the largest, etc., etc. Okay. And if nothing works, I have a normal form. So let me, it's a little bit cumbersome, but still let me write this algorithm like in pseudocode. So it will be very clear what we are doing. Okay. So I think this writing algorithms is always takes a lot of space, but okay, I do it anyway. So now let me state the division algorithm. Division algorithm. Okay. I have to say what is the input. Okay, on the one hand, this collection of non-zero polynomials, always in many variables, and the polynomial f. The output, these coefficients a1 up to ar that appear in the lemma, and the remainder g. Okay. So, so the question is which programming language to use. Okay, it's not defined, but you will understand. Let's say it starts. Let's begin. Okay, begin. So I initialize, so I have, so I think like A1 up to AR are local variables. So maybe I write it this way. So they are assigned the initial value 0 and the G as well. So this is initialization. And I have an auxiliary variable P, which will be a polynomial, and this is assigned F at the beginning. Okay, and then I have a while loop, while, okay, while P is not 0, do. Okay, I have some counter. Okay, the counter is an integer, so initially it has 1. Okay, and then I have I have a Boolean variable, division occurred. Maybe I write it here. Division occurred. It's a Boolean variable. Okay, this gets the value false. So far, no division occurred. Okay. Right, and then another loop. So while. Okay, now what I try to go through the list. So while my index I is less than or equal R and division occurred false. Okay, this is such a long variable, it's terrible. Division occurred equals false. Okay, well, I do the following. So I check whether the leading term of Fi divides the leading term of P. Okay, so at the very beginning of the algorithm, P is F. So I check whether the leading term of Fi divides the leading term of F. Okay, so if this is the case, then, okay, I define the term U, or monomial, sorry, U. It's going to be leading monomial of P divided by the leading monomial of Fi. So this will be a monomial because I have the divisibility. And then I update AI. So the new AI will be the old AI plus U. And I subtract from the current P, U, Fi. So this is just a formal way of expressing what we do in this algorithm. Okay. Takes a little bit of thinking to see that this is right we're doing, especially with regard to the UI. But you see, I mean, hopefully this you understand exactly what we're doing. Then we at the very beginning, here we have the F, and now we subtract U times Fi in order to kill this term. Okay. And then if this has happened, I update my Boolean variable. I say division occurred becomes true. True. Actually, yeah. Okay. So, right. This was if, then, blah, blah, blah. Then is an else. Okay. So if I'm here, I couldn't find an I to do that. So I was not successful with Fi. But then I upgrade. Okay. I just increase my counter by 1. So I started with I equals 1, say it did not succeed. I try with I equals 2, etc., etc. Okay, so I do this and so this is the end of the if. Okay, maybe. Okay, maybe if I write stars, I mean a comment just to make clear the logical structure of this program. So this was the end of the if. Okay, and then there is the end of the while. End while. Okay, so when I'm here, right. So I went through this thing. Then I check where the division occurs is false. If division occurs, equals false. So then, right. So in a way, I couldn't find any. Okay, it was not the case that any leading term of Fi did divide the term of my F. So then what I do, okay, let me write G is updated this way. And P is updated this way. So I hope I can explain why this is the case. Right. Right. So in a way, I had my P and I was not successful in removing this leading monomial of P. Then I take it away and say, you will be part of the remainder. Okay. That's why I add it here. Okay. So I cannot treat it further. It will be part of the remainder. I subtract the leading monomial of P, and then I continue with that one. Okay, so the program is now finished. Now this is the end of my this if. Okay, and then I have end while. Okay. Okay, if you do programming, then it will be easy from convert this in an actually program and end begin. Okay, and I didn't say what I mean from I'm not very formal, but I think it should be clear the output is now the output is the A's and the G's, and these are the I mean when the program stops, these are the values that I have when I finish. Okay, so whenever you have such a statement of algorithms, there should be a theorem about it, and it says the algorithm terminates first. Terminates, okay. For the output, so this is now I write what we want. Actually, we have f reduces to g. G is a normal form. Mod f. And I have this representation such that, okay, as in the lemma, leading term of fi is less than or equal leading term of f for all if ai non-zero. Okay. So in principle, now I should prove the theorem, but this is not an algorithms class, so maybe I will not do it. Right, but if you ever have seen such a thing, I mean, you have to, algorithms are not static, they are dynamic things. So you have to, if you want to prove it, you have to make a statement which you prove remains true in every loop, okay? So that's the way to prove it. But I think I'm not going to prove it formally. It's not hard anyway, but it's just a way of, right. Have you ever seen such a thing? I mean, maybe in coma, are there such proofs that algorithms
Yes,
behave as they should?
of course.
Of course, right. Okay, then I don't have to do it here. Then I don't have to do it, but it's straightforward. There's no problem. Okay. Okay. Right. So then also I think it should be clear that this just generalizes the usual division with remainder algorithms that you know for polynomials in one variable. It's just generalizes that. And maybe notation. Okay. So okay, I denote by this. Okay, this is this denotes the output of the algorithm. Okay, this is unique. Okay, it's not a nice mathematical object, but once the polynomials in this set F, I mean, if I order them, then I have this unique output. Okay, denotes, this is the output of algorithm. Call it remainder of division of f by this f. And this is important. Okay, maybe I should write it as a sequence. So this is ordered. Otherwise, it would not be defined. Okay, but once it's ordered, it's defined. Okay. Right. Okay, so before I can introduce Grübner basis and then everything will be nice, I need some more theoretical preparation, okay, that I do now. So you need to be a little bit patient. So let me make another definition. So what I have, I had this one-step reduction, okay? And this one-step reduction defines an equivalence relation, okay? And this is what I'm going to define here with this symbol. So now I have arrows in both directions. I put an F, maybe here an M. So this means, let me write, there are polynomials f0 up to fm such that f0 is f, is the first one. The last one, the fm, is the g. And for all I, okay, you understand for which I. So either fi reduces to fi plus 1 in one step, or backwards, or this way. Let me write it. You will understand. So you have a chain of a sequence of polynomials. You start with f0, end up with fm, but in every step, the reduction can be forward or backward. Okay, that's the definition. Okay. Then I say, okay, if I don't specify the number of steps, I just put the star. This means there is some m natural number such that this holds. Okay, good. So this is a definition, and we note that remark. So this is a equivalence relation. So I think it's obvious. I mean, it has all the properties of an equivalence relation. This is the equivalence relation. Okay, the one generated by this one-step reduction. Okay. Right. Okay. So now, okay. So actually, what is this all about? Okay. We are working in polynomial rings, and we are studying ideals. Okay, we will study ideals, and one major problem is, computational problem, is to decide whether a polynomial lies in an ideal or not. Okay, how can I decide that? Okay, so the ideal is generated by a list of polynomials given by the set capital F. And then I have this polynomial small f. I want to know, is it in the ideal? How would I, algorithmically decide this? And I want to decide this using these reductions. Okay. Now, if I have this as an auxiliary notion, I have this two-sided, I have this equivalence relation. I can now characterize this really nice, in a nice way. So it's the next lemma. Okay, so what do I have? I have f and a, these are polynomials. And the fi is also, no, what is fi? Right, fi is in my set capital F. Okay, I have fixed my set capital F as before. Okay, there are two statements. So one is f. If I add to f a multiple of fi, okay, then this is equivalent in this sense I just defined to f. Okay. And the second statement is f lies in the ideal generated by capital F. So this is the ideal generated. Maybe I write it because I think, never formally defined it. So this is the ideal generated by the set of polynomials F. This is the case if and only if F is equivalent to 0. Not F. Okay. Maybe at this point, not clear why this is useful at all. You have to be patient a little bit. Okay. Okay, let's prove it.
To be sure, I have a question.
Yes. Mhm.
There, by the definition of this equivalence relation, shouldn't it actually be for all I these or for all I this? Or do we really mean what is written here?
I mean, for all I, maybe I make it a
It
little
is
bit
either
more.
all in one direction or all in another direction, right? Not
For
that we
all
can...
indices I greater than or equal 0, less than m, I mean, in parentheses, this or this. Ah,
But I mean, really, we can go in one and other direction in between, because that is what...
yes, yes. So maybe, okay,
Okay,
maybe I can. So I mean, like you are here. This is F0.
okay,
Now, I mean, obviously, maybe you try to go here in this, but maybe you don't do that.
okay.
Maybe you do this. This is okay.
Oh, okay.
Okay, so this is right. And then you go maybe F2. This is also okay. And then maybe the F3, you go here. Up to you.
So
I mean,
really like that. Okay.
I want that. Right. So this is the only way I can get an equivalence relation.
Okay.
Okay. So, okay, the proof of this lemma. Okay, let me think. Okay, so I have f. I add a times fi. Okay, and I want to show this, what I get is equivalent to f. Now, easy to see without loss of generality, ai can be a monomial. So a, no, sorry, not ai. A can be some coefficient times a term, t term, lambda, some non-zero coefficient. Because if I have proved statement 1 for these special a's, I can just apply it several times, okay? Because I write a as a sum of monomials, and then I do it several times to get it, okay? So it's enough to do it in this case. Okay, now it's like, now we have a case distinction. What did we, okay. Assume, okay, let's assume the term t times leading term of fi occurs in f. Let's assume this is the case. Say with coefficients, some coefficient mu, non-zero, and okay, lambda plus mu is non-zero. So I'm a bit pedantic here, but let's assume this. Okay, then I claim, maybe I can explain it a bit clearer terms, but I claim then, so maybe before writing what I claim, maybe I should explain also, maybe in little green, what's happening. Okay. Right. Okay. So. Okay, maybe better to write the statement and then discuss it because it's not that hard. Mf plus lambda t fi. I claim I can reduce it in one step to f minus mu t fi. Okay, why that? yeah, I think. So, okay, maybe now I explain in green. So if okay, I assume I have mu t leading term of fi. So this is a monomial occurring in f, okay? So f is this. I mean, I write all these monomials in descending order. This occurs, okay? Okay, and then what do? I just add this. Okay, I add this, so the leading term here will be leading term of fi plus da da dum. So this will be lambda t fi. Okay, and if I add them, I mean, yeah, I just combine. Yeah, you see, just combine them. Okay, and so what I have here is this mu plus lambda t leading term of fi. So this is what I have for this polynomial. Okay, and now you see I can reduce to that, because how can I reduce to that? Well, I kill this. Okay, I'm gonna kill this thing. Okay, kill this. Okay, and if I have killed this, what does it mean? I subtracted this. So what I get in the end after subtracting it, I have this. Okay. Okay, it sounds a bit complicated, but it's actually very simple. Okay, but how can I get? But now the observation is, I can also go from F, like in the other direction, to this. Okay, now I'll just look at F. I just look at my F. Where is it? Sorry, I just look at F. Okay. And then I only reduce that term. Then I'm here. So this is also possible. So this is not a complicated, it may be confusing, but it's very simple in a way. Write it down for yourself, figure it out what it means. It's very, very simple. Okay, so what we have seen in this case, I have the equivalence. F plus lambda t fi is equivalent to F. Okay, but you see, I needed to go in the backward direction. The other case is analogous. Analogous. Very similar. There's no point. It was the most interesting case. So this is the proof of the first claim. And the second one. So what is the second one? F is in the ideal if and only if it reduces to 0. So one direction, very simple. So, right. Because, okay, just use this. If F reduces to G, mod F, then I always know that F and G are congruent modulo the ideal generated by F. Actually, this is very important, so maybe I should have emphasized it more clearly. So if you see, maybe I go back. Okay, I didn't emphasize it very clearly, but it was, when did I do it? When I did this lemma. Okay, when I did this lemma, actually, I do a reduction. You see a reduction. I get this representation. So what I see, F minus G lies in the ideal generated by the Fi. Or I could say F is congruent to G mod F. So maybe I should write it here in. Okay, this is always, okay, a consequence. Okay. So I have this. Oh, sorry. So I see now if I do one-step reductions, I remain in the same residue class. And if I do it many times, it doesn't matter which direction, it's okay. Because you see on the right-hand side, this is an equivalence relation anyway. So this shows this direction, the other direction. So what was the other direction? I have an element in the ideal. I want to show I can read. Okay, it's equivalent to 0. So what I do, so if f is here, so this means there are AI coefficient polynomials such that f is some AI fi. Okay, now apply 1. Okay. Part 1 says this. So you apply part 1 several times. Okay. You start. Yeah. 0 is congruent. 0 is equivalent to 0. So A1 F1 is congruent to 0. A1 F1 plus A1 plus A2 F2, etc. etc. Just apply it several times. Okay. Right. Any questions on that?
Doesn't the second part also follow from this F congruent G directly?
From which? From?
Like the second part, if
Yes.
we have that F is in the ideal, then F should be congruent to 0, modulo F,
Right.
capital F, and isn't that directly implying that we have that F reduces to 0?
But I think but we still need what I showed in the first part, I think.
Okay.
At this, I'm not saying that what I'm doing is in any way difficult, but I don't think it needs some argument, I think. Okay. Okay, but now finally I can define the concept of the Gröbner basis, and I think that's that's a real highlight. It's important. It's nice. I would say it's a nice thing. So next section, Gröbner basis. Gröbner basis. So Wolfgang Gröbner was an Austrian mathematician working in algebraic geometry. And right, he had a student, Bruno Buchberger. Yes, he wrote his thesis on that and he coined that name. Okay. So, okay. Like Buchberger made Gröbner famous by coming up with this notion. Extremely useful notion. Okay, so we fix a term order on our terms. And I'm going to assign definition. So I have an ideal. Let I be an ideal in my polynomial ring. Be ideal, an ideal. Okay. Now I assign to this ideal a monomial ideal, which will be called leading ideal or initial ideal. There are different names. And how do I do it? Okay, this is a definition. LT is like in Cox little of she with the capital L, leading ideal. So this is the ideal generated by the leading terms of all elements of the ideal. So I take any f, any polynomial in my ideal I, it should be not zero, otherwise there is no leading term. Then I look at the monomial ideal generated by all those, and this I call leading ideal. It's called leading ideal of I, and of course with respect to the term order. So one should be aware that this is not like a complete absolute invariant notion. This is only defined after choosing a term order. If you change your term order, the leading ideal changes. Okay, this is the leading ideal. Just okay for the pedantic convention. I mean, if you have the zero ideal, I mean, what should it be? Okay, then I define it to be the ideal generated by the empty set, and this is by definition, it's just zero, just to make, okay. So we don't have to exclude this case. So this leading ideal is a monomial ideal by definition. And we will see that it contains a lot of the information about the ideal. In a way, it's very important. Ideals can be really complicated. Monomial ideals are much simpler. In a way, monomial ideals are combinatorial objects. Not that the combinatorics is simple, but it's more concrete. And it turns out that this process from going to the ideal to leading ideal, most of the information is just preserved. Okay, I cannot make this rigorous at the moment, but it's the case. Okay, but there is, okay, one has to be careful here. Again, warning. There are pitfalls, warning. So let's assume my ideal is generated by polynomials f1 up to fr. Okay, then, I mean, what is clear, if I will now look at the monomial ideal generated by the leading terms, clearly, this is contained in I. This is clear repetition, but we may have strict inequality, but may have strict inequality. So in order to compute this computing the leading ideal is not obvious how to do it. You cannot just start with any generators and take the leading terms of the generators. It will not be enough. Now, here is a simple example. Very simple example showing that this may happen. So what do I take? F1 is x squared plus y. F2 is xy plus 1. Okay.
Sorry, I think
Yes.
you mean in the warning, do you mean it's a subset of the leading ideal rather than the ideal itself?
Correct. I wanted to okay, thank you. Yes, so and I graded lexicographic ordering. This defines my term order. So these, if I mark just the leading terms. This will be the leading terms. Okay, now I compute. Okay, leading term of F1, leading term of F2. So this is the ideal generated by x squared and xy. Okay, I could make a drawing, but maybe it's not helpful at this point. But now I take this linear combination f equals y f1 minus x f2. And then we see we have some canceling. Maybe let me calculate here on the side because it's really helpful to see. F1y. So I have x squared y plus y squared. Okay. And xf2 I have x squared y plus x. Then you see, okay, these two terms appear for both polynomials, and if I subtract, they are killed, okay, eliminated. So what I get is y squared minus x. Okay. Okay, and this guy has the leading term y squared. Okay, the leading term. Okay, maybe this should be white. The leading term of f is y squared, and that's not in this ideal. This is 2 actually. Okay. Y squared is not divisible by x squared, and is not, sorry, x squared doesn't divide y squared, and xy doesn't divide y squared. So this is an example. Okay, so there is something going on here that may be tricky. Okay, and now comes the definition of a Gröbner basis. Okay, what is a Gröbner basis? Right, this will be a set, a finite set of elements of the ideal with the property that here I have equality. So those generating sets with this, where equality holds, these are the nice generating sets. They are called Gröbner bases. Okay, here is the definition. Important definition. Let I be an ideal in my polynomial ring. Okay, a Gröbner basis. Sometimes I just say G basis to save some of my writing. A G basis of I with respect to the chosen term order is a finite subset G of I. Actually, I don't want to have 0, such that, okay, right. So the leading ideal is the ideal generated by the set of leading terms. Okay, how do I write it? Okay. Maybe let me, okay. Sorry. Here I put leading term of G1. Okay. This is the Gröbner basis. Okay. And then, okay, if you have the 0 ideal, then you say, okay, maybe for the pedantic, empty set is Gröbner basis of 0. Okay. So let's see. Actually, it's good to have a notation. I want to save some writing. So I just write LT of G. This will be just a shorthand. Now this is a set, it's not the ideal, it's just a set of leading terms. So, right. If G is this. So this is convenient. You should not confuse. Okay, so I have this notion, leading ideal of an ideal. It's a monomial ideal. And then if here I have a finite set, then I use also this LT, but I use it with not with capital letters. It's just the collection of leading terms. So this will help me some save some some notation. So first observation is, you may have noticed in this definition, I did not require that the leading terms of these, or I did not require that these G's, that the set G generates the ideal. This is automatic. So this lemma says a Gröbner basis is a consequence. A Gröbner basis G of I generates the ideal. Okay, so this will be a consequence of the definition. Let me prove it. Okay, so let's say, okay, so I give, okay, the ideal generated by G, I give it a name. Let me call it J. So J is a subset of I. Okay, I want to prove J equals I. Okay, so this inclusion is clear. So let now F, okay, be in I. So what I do now, I reduce to normal form. Say F reduces to H, modulo G, and H is a normal form. Mod G, normal form, mod G. Okay. So then I certainly know, then I know F is congruent H modulo the ideal generated by G, which is J. Okay. Okay, so it's clear. So it's clear my H is in J. No, is also in I. H is also in I. So now I have replaced F in I by the normal form. I have a normal form in I. I want to prove that this H must be 0. Okay, then I'm done. Right. So let's assume now by contradiction, assume H would not be 0. What would happen then? But then the leading term of H would be in the leading ideal. Because that's how the leading ideal is defined. Okay, it's the ideal generating by the leading terms of all monomials in the ideal. Okay, of all polynomials in the ideal. I have a polynomial H in my ideal, non-zero, so its leading term must be there. Okay, this because I have a Gröbner basis, this is the generated by the set of leading terms of G. Because I have a Gröbner basis. Okay, but this, now I have a contradiction, but H is a normal form. Mod G, and this is not possible because being a normal form, we know this means this is not here. Okay, if this were here, I could make a reduction. Okay, I could do a reduction step. Well, I assume it's a normal form. This is a contradiction. So I showed H equals 0, and therefore F is in J. Okay. So I showed, okay, showed, maybe I can write it. I showed J equals I. Okay. Okay. Okay, so this maybe was not so exciting, but the next result, I think this will be exciting now. Okay, my last board theorem. So this is, I think, a really nice theorem. So first of all, every ideal has a Gröbner basis. Every ideal, let's say I in the polynomial ring, maybe let's write explicitly, has a Gröbner basis. Gröbner basis. So they exist. Okay. Bezüglich, okay. Okay, maybe I should say with respect to any term order. Again, you fix your term order, you have a Gröbner basis. It's dependent on the term order. And two, every ideal in the polynomial ring is finally degenerated. Every ideal, okay, in the polynomial ring is finally degenerated. Okay, so people say this means the polynomial ring is Noetherian. Okay, third property. Okay, this is there is no infinite properly descending chain of ideals in the polynomial ring. There is no infinite properly descending. I mean, strictly descending is better. Strictly descending, strictly. As I did, okay, I said descending, but I wanted to say ascending, aufsteigend, strictly ascending chain of ideals in the polynomial ring. Okay. So let's see. How do we prove it? The proof is now, I mean, it's everything is basically done. So let's see. First statement. So I have my ideal I. I look at the leading ideal. This is a monomial ideal. And then I apply Dixon's lemma. This is finally degenerated by Dixon's lemma. Okay. Okay. So I pick a finite system of generators. This is a Gröbner basis. And the Gröbner basis generates the ideal. Okay. Okay. Okay, say, so there are, maybe I write it. Such that this is generated by this. Okay, so this means okay, this is a Gröbner basis of I, and we know it generates I. Because we just, this was our lemma just above. Okay. So, okay, I think I will need I want to have a little bit more space somehow. How did I do it? No more space. Oh, here. Okay, got it. Sorry. Okay, proof of two. Every ideal is finally degenerated. I mean, okay, I is generated by a Gröbner basis. Of I will be proved in one, there are Gröbner bases. Okay, and the third thing is a very standard. Maybe you have seen that. It's completely standard. So maybe I should write it for the sake of completeness. So let's assume I have a ascending chain of ideals. Ideals of the polynomial ring. Okay, I want to show it must become stationary. Okay, there is some index. From that index on, the ideals will not get bigger anymore. Okay, so what I do, I look at the sum of all the ideals. I write it as an infinite sum, you know what, but you know what this means. We discussed it. This is the ideal generated by all these AJ, okay? Maybe this should be J, nicer, okay? Okay, but this must be, it's an ideal. It's an ideal, so it's finally generated. Okay, by part 2, every ideal in the polynomial ring is finally generated. So it's finally generated, say by elements F1 up to, I don't know, Fm. Okay. So the F1 lies in one of these ideals, maybe, I don't know, in I don't know, IK1, F2 in IK2, and etc., etc. But these ideals are, okay, they form a chain. So now very easy to see, there will be some index n such that all these generators, F1 up to Fm, lie in In. Okay. And then I see that the sum of all the ideals here must be In. Okay. And I see there's nothing happening anymore after n. So In equals In plus 1 equals In plus 2, etc. Okay. So this chain becomes stationary. So there is no infinitely strictly ascending chain. Okay. Right. And so this property 2, and which is equivalent to 3 actually, is called Noetherian. So remark. So there are two things that I want to say. So statement 2, every ideal in the polynomial ring over a field is finally generated, is called Hilbert's basis theorem. Called Hilbert's. Okay. Hilbert's basis theorem. Okay. So we proved that. And right. So property 2, which is equivalent to property 3, but I only proved one direction, is called means that the polynomial ring is Noetherian ring. Okay, later on, I want to discuss this notion in full generality, but for the moment, I just noted it's called this way. And we proved that polynomial rings are Noetherian. That's a very important result. Okay. Any questions? Okay, let me ask you, oh my God, I missed this. Okay, I wanted to ask a question. Okay. How about, what are the simplest ideals? Principal ideals. So maybe a remark. Let's say I is a principal ideal. This is generated by one element, principal ideal. Okay, let's say G non-zero, otherwise it's completely trivial. So what is a Gröbner basis of a principal ideal? What do I do?
Take
It's
the leading term of G.
Yes, sure, yes. Then just G, I mean, is a G basis. It's a Gröbner basis for I. This is trivial. So you see, if all the ideals were principal ideals, then life would be simple. We wouldn't need this concept. So this concept of the Gröbner basis only becomes relevant for ideals that are not principal ideals. Okay. Well, and the other case, another case is, it's also trivial, but it's good to note. Okay, it's right. If I have a monomial ideal, okay, assume G consists of monomials. Okay, then G is a Gröbner basis. Is a Gröbner basis, G basis for this ideal. Right. There can be no funny cancellation. I mean, you, right. Is it clear? I mean, if I I take an element, I take an element here, I take a polynomial here. Then I take its leading term. But because this is a monomial ideal, I know if a polynomial is in it, all of its terms must be in it. So the leading term must be here. Okay. So one of the G's in the capital G will divide the leading term. And that's the property that we need. Okay. So this concept is right. So in a way, I mean, this is a very simple observation that this is true. But it is right. But it is false if I have general ideals. But somehow this concept of Gröbner basis allows to, save this. Okay, I think what will we do next time? Okay, so I mean, there will be good news. So we learned what the division algorithm. And I said one bad thing about it is this remainder is not even uniquely defined. But now we will see that if I make a division, I apply the division algorithm and I divide by a Gröbner basis. So this capital F set will be now a Gröbner basis. Then it turns out that the output of the algorithm is unique, independent of the order of the polynomials. It doesn't matter. So I get unique normal forms. So this is very, very nice. So I arrive at something independent of what the algorithm does. Okay, so this is very useful. And right, but what I also want to discuss is, right, we showed that Gröbner bases exist. Okay, that's nice, but maybe you want to compute some. So I will also show you how can one compute the Gröbner basis. So this is called Buchberger's algorithm. It's a very simple algorithm. It's not very sophisticated. It's easy to explain. Unfortunately, it's not very efficient. So, right. One bad thing about this story is, even though it's theoretical so nice, is these Gröbner bases can be very big. So, I mean, you can solve many problems in ideal theory, but you can only solve it in principle because these objects can get so big. Okay. Right. But I think this will be the topic of next week's lecture. Okay. Are there any comments or questions?
Yes, but this question is kind of like a question out of interest, not about the lecture. So if others have questions about the lecture, it's better when they ask first.
Okay. So I mean, I think then maybe I stop this and I will stop the recording.